we will be discussing about simulative annealing. In short, I'm writing as simulative annealing. So, what is our problem actually? We have other algorithms as well, but the problem that we encounter with is stucking in local optima. We have some optimization problem. It can be minimization, maximization, depending upon the nature of the problem, that it is minimizing or maximizing. But what actually happens is the algorithm stuck in local optima, but what we actually want is global optima. So the point here is, in a hill climbing, I'm writing just at C. In a hill climbing algorithm, what actually happens is that there is a point and the algorithm moves towards in upward direction towards that optimum, but it do not know that whether it is global optimum or not. It's just moving towards the optimum in its present given space. So what a hill climbing is doing is it's doing exploitation. What happens in exploitation is that it explores the given knowledge. But on the other hand, you must have encountered with a term known as random walk. Random walk, what happens that in a given space, it randomly do movements from one point to another in the whole given search space. So random walk is actually doing what? It's actually doing exploration. So it's actually doing exploration. It's exploring the whole search space without evaluating that whether the point is moving towards is better or not. So what we need is we need both exploration and exploitation in order to get out of local optima, which usually happens in will definitely happen in hill climbing because it do not have the knowledge that maybe somewhere else there will be present a global optimum greater than this one. And in a random walk, that is never in random walk is never going to get some optimum solution. It's just walking randomly without any evaluation from here to there. So we need a combination of exploration and exploitation. The optimization doesn't necessarily happen in just computational world, it also happens in physical world. In physical world, we encounter with what? Materials. And materials have some properties, and the properties are defined by their underlying arrangement of atoms, that how these atoms are arranged. If the atoms are tightly bound, then we're going to have a strong material such as ceramic, and the different arrangements of atom demonstrate different properties of that material. So it means by changing the arrangement of atoms, we can have better materials of our choice. So for this, what we need to do is we need to change this material into liquid and then cool down to turn it again in solid form. But in the process of this cooling, we will be doing it in a controlled manner such that its cooling will be under our control, that how the atoms are going to make arrangements, or how they are going to make the underlying structure. So this process is known as annealing. Okay, how this annealing is related to our topic, I will be discussing this later. So the next thing is, what we said, we usually have, let's say we have a current node C and it has some neighbors, and we will be doing some exploitation that if we look into a neighbor and such that there is a node N in its neighbor, it will check that whether it's better to the N is better to C or not. In hill climbing, what will happen if we'll see if the fitness value of N, obviously for both nodes we will be having some evaluation because we are calculating these values for some function. Then we are going to have some values for these nodes. We will be having some evaluation value for N, point N, it will be having some evaluation value, and as well as C will be having some evaluation value. In hill climbing, what happens? The difference will be calculated if n has greater value, then the algorithm will move from C to n, otherwise it will not. But what will happen in random search, random walk? In random walk, it's not going to check any evaluation value, it's just going to randomly walk from one point to another. But what we don't want to exactly move towards n with the probability of 1 or 0, and we neither want to move randomly without any evaluation. What we want is we want some probability with which the point should move from C to n. So, and the other thing is to control this probability, that with which probability C should move to n, we want some another parameter. I will be discussing this later. Talking about this probability, is some function which obviously have values between 0 and 1. This function is actually exponentially increasing or decreasing between the values 0 and 1. Let me write this function. This thing means probability of moving C to n is equals to 1 over. Now here is a point that I need to discuss. What we do is actually we find the difference in the evaluation values of the both nodes, which will be, we need to find the difference values between the evaluation values of both of these points. For this, what we have del E is, let's suppose, the difference between the evaluation of n minus evaluation of C. So if this thing is positive, it will move from C to n with some probability, and this probability will be calculated as 1 over 1 plus e power minus del over e. Now, as I said, I need some second parameter to calculate with which probability C should move to n. This is t. Now let's study its behavior, the behavior of this function, to conclude its properties. Let's take a current node with a evaluation value 100 and a constant temperature of T, which is 10. Obviously this T we are going to call it temperature. With different values of n, there will be differences, as it is minus del E, and there will be probability. Let's take n value is 40. Its minus del E will be 60, and with this value, its probability is 2 into 10 power minus 3. I'm ignoring the points. Now let's suppose for 18, minus del E is going to be 20, and its probability is 0.1192, and so on. Now for 100, if the value of n, the next node, the evaluation value of next node is 100, minus del E is going to be 0, and its probability will be 0.5. So let's suppose if the value of n is 140, its minus del E will be minus 40, and its probability will be 0.98, 2, and so on. And if its value is 180, let's suppose, its minus del E will be minus 80, and its probability of moving from C to n will be 0.999. So we have seen this, that with the increasing value of n, especially greater than the value of C, we have probability of moving from C to n, which is increasing towards 1. The probability is approaching towards 1, and for the decreasing value of n, the probability is approaching towards 0. So this is the effect of the value of n. Now let's talk about what will be the effect of t. Let's take one example from this. From here, let's take 140. This value, if n equals to 140 and c equals to 100, and now let's change the value of t and check the probability for different values of t for these points. That's what's its effect. Let's take it 1. If the temperature is 1, its probability of moving from C to N is 1. Next, if the T is, let's suppose, increase the value of T, it's 3. Its probability will be 0.9999 and so on. Okay. If the value of T is, let's suppose, 10, its probability will be 0.9820 and so on. If the value of T is, let's suppose, 100, the probability is going to be 0.598, and eventually for the value 10 power 10, the value of T 10 power 10, its probability will be 0.5. So what we conclude from this, that with the increasing value of T, what happens is the probability of point moving from C to N decreases. So with the help of T, we can control the probability of the movement from one point to another. So actually what's happening here is there are two loops. In the inner loops, we are checking its neighbors. We are checking the probability of neighbor points with some t. T, let's suppose, equals to I for all neighbors. This is the one loop. And in the outer loop, what's happening is for different values of t, we are checking all the neighbors of the point C. Okay? In the under loop, what's happening is the neighbors are being checked, the probability values of neighbors for particular value of t, and in the outer loop is what's happening, the value of t is changing, and obviously for every value, every neighbor is probability of every neighbor is calculated. This algorithm is known as simulated annealing. So what is the significance of introducing this term temperature, and what does this actually, how does it work? Let's study this. But before this, let me introduce you people a website known as desmos.com, where you can visually see how this function behaves. Here in desmos.com, just search about it and go to its calculator, and here write the function. I have wrote the function, and you can see that with the changing value of t, the function is going to be to behave differently. What's happening with the increasing value of t, it's become flatter and flatter. The function is becoming flatter and flatter, but keep in mind that the values are between 0 and 1. But by decreasing the value of t, it becomes steeper and steeper, and on 0 you can see that t equals to 0, it's acting like a step function, and with the increasing value it's becoming flatter, and with the decreasing value of t, it is becoming steeper and steeper. And we can see that for the value of t 10 raised to power 10, its output is going to be parallel to x-axis. Like for every value, it's going to give us 50% probability. Now let's come back towards the point that in simulating annealing, what we are doing is, in the outer loop we are changing the temperature, inner loop we are calculating for that temperature, we are calculating the probabilities for each neighbor. So how it's going to work? Let's take a function. Okay, actually simulating annealing, what we'll be doing is we will be setting the value of t very large, and then we will be slowly and gradually decreasing the value of t. By decreasing the value of t, we will be controlling the probability with which the point can move from one to another. Okay, the algorithm can move one point to another. So in star, there will be entropy. With the large value of t, there will be entropy, there will be more randomness, and the points will be moving from here and there, and maybe points moving towards the other point with less evaluation value. But gradually and slowly, by increasing the temperature, we will be controlling this behavior, and then later on the points will only move towards the points with having the large evaluation value. Okay, let's take snapshot of this function. Okay, what actually is going to happen is, this is the function, the part of the function. There are 3 points. Let's suppose A, B is here and C is here. What we want is to move from A to C, because we can see that it's our optimum, global optimum. But for this, first we need to go to B and then to C. In maximization problem, in our algorithm, its natural tendency to move upward, but going downward is it's like going against the energy level. The energy level here will be AB, and the energy level here is BC or CB. Okay, so what do you think? At high temperature, at T equals to large, what will be more easier, to move from C to B or to move from A to B? Obviously, to move from A to B, it will be more easy. So in star, the temperature will be large and the points will be moving against the energy levels from here and there, because there will be large randomness. But gradually and slowly, we will decrease the value of T such that this point will be at here. Now we are at B point, and with the small value of temperature, it will obviously move towards the higher value. It will move upward and it will move towards the point C, which was our global optimum. Or right now in this snapshot, this is our optimum. This is how this whole algorithm works. That we in the inner loop, the probabilities of the neighbors, we are finding the probabilities of the neighbors and moving from here and there with the large temperature. In start with the large temperature, there is more randomness, entropy, and the points are moving from one point to another here and there. But gradually, by decreasing the temperature, to make sure that now they will definitely move towards the optimum. So this is how the simulating annealing works, and this is how it is connected with the annealing process which happens in physics, which I have already discussed. The annealing process, what we do is, we first liquidify the material and then we solidify it with a controlled cooling process. Like we cool that material in a controlled manner, in which direction, what the structure, according to what structure we want. Similarly, now here we are decreasing the value of T, or you can say decreasing the temperature, in a sense what we want. Now we want our point towards move towards the optimum, and that's what's happening here. And this is how we find our solution. I hope this is clear, and if you have any questions, you can check my website as well. There will be a post for you and you can comment there. Thank you.